In a pool, you have fast swimmers and slow swimmers. Fast swimmers have little resistance, while slow swimmers have a lot of resistance. Now imagine this pool as a field, and the swimmers as particles. Some particles interact a little bit and breeze by, while others interact a lot and are slowed down. This is called the Higgs field. This theory, proposed by Peter Higgs, was how he thought particles got mass. Water resistance appears as waves and splashes when a swimmer moves through it. In the Higgs field, these wave ripples are called Higgs bosons. But why is this boson and field important? Let's say I gave you the smallest piece of this apple. You would have a fundamental particle. And we actually have 17 of these, which we call the Standard Model. There are 12 fundamental particles that carry mass. We call these fermions. And there are 5 more fundamental particles that carry forces. We call these bosons. The Higgs boson is important because it's the final piece in the Standard Model. But why do some particles have mass and others don't? This is where the Higgs field comes in. Higgs proposed that particles get mass by interacting with an invisible field called the Higgs field. Depending on how much a fundamental particle moves through the Higgs field, Higgs bosons will latch onto it. So in theory, the fundamental particle gains mass. Similarly, waves latch onto a bad swimmer, making them feel heavier. But in 2012, it was discovered. The Higgs boson had been found. Again, why is the Higgs boson and its field so important? If particles get mass from Higgs bosons, then everything in this universe needs it. Without this God particle, atoms wouldn't exist. With the discovery of the Higgs boson, scientists have realized there are far more particles that could fit the Standard Model. 100 years ago, the only 2 fundamental particles we knew were the electron and the photon. Imagine the next 100 years. The Higgs boson is not the end. It's actually a beginning, a breakthrough.